We're going to talk today about separable differential equations, and the key here is, of course, the word separable. It gives away what's happening. There's this idea of separating. Now, if you think about what a differential equation is, it's A equals B, right? We have two parts, and we have two variables, often y or x, but it could be x or t, x, whatever it is. So two variables, two sides to an equation. The idea is we pull them apart, and so that we have all of the y's on one side, all the x's on the other, and life can be good. Okay, so let's go through and talk about the process. So in particular, we say, look, we have a differential equation, and it can be written in such a way that we're able to rearrange. Now, one of the things that often comes into play is saying, what's the right technique if we see a problem? Now, today we're in the mindset, oh, we're in separable differential equation mode, right? So everything we see, we're going to say, separate, separate, but on an exam, we're not in that. We're just like, here's our problem. Like, what do we do? Well, you got to figure it out. So oftentimes, the key here to look for is, if you look on this side here, what you'll see is lots of multiplying. So separable differential equations tend to be one where you see lots of multiplying happening. Why? Well, because you need to separate. Now, that's our first step. And the way you separate is you divide or you multiply. You move things around. And so you need to have lots of multiplying to be able to do that kind of movement. All right, so here's our step one. You separate. Now, I want to be clear here that you really want a very particular form, namely y prime over g of y equals f of x, or if we relax with our notation a little bit, because y prime you can think of as change in y over change in x, dy dx. Now, technically, dy over dx is not two things, it's a stand-in for one thing. And but if we say, well, let's just relax and let's just say, okay, suppose it were two things, dy over dx, we really want to separate so we have all the things with y on one side, all the things with x's on the other side. Now, it's not just a matter of saying, oh, all the y's on one side, all the x's on the other side. So, for instance, if we wrote something like y prime plus y equals x, this is not separable. Even though you say, well, wait, all the x's on one side, all the y's on the other side, why isn't it separable? Because the key here is we really need to get it things with y times dy equals things with x times dx. So that doesn't fall into that category. Now you might say, can this be solved? Yes, but using other techniques, which we'll talk about in the near future. Okay, so we've carried out step one. We have separated. Now goes to step two. Step two is to integrate. And if we think about it, really a differential equation, at the end of the day, there's an integration that's going to show up somewhere. And the question is, how do you get to it? And so as we talk about different techniques, it's all a matter of how do you get to the integral. And we say, okay, well, now we integrate both sides. And, okay, I like this format here just because it's easy to see. So we have the integral dy over g of y is the integral fx dx. Now, when you integrate, these are indefinite integrals, what do you need? Well, you need a constant, a plus c. Whenever we solve a differential equation, there's always going to be a plus c showing up somewhere. And so we need to be mindful of what that plus c is. Now, you may have said, well, wait, hold on. You had two integrals, one on the left, one on the right. Shouldn't there be two constants? Ah, okay, I see where you're going with this. No. Now, the reason we don't need two constants is because if we say, well, look, there's a plus c on the right-hand side, there's a plus c on the left-hand side, or maybe I should use the letter d, what we can do is we can move the constants over and they can merge. Or as I like to think of it, as constants are like sponges, right? So that we can absorb two constants into one sort of uber constant. And so we just need one constant involved. All right, good. Now, there will become times when we might need more than one constant. So I don't want to say this is a hard and fast rule, but just keep track. A good rule of thumb is whenever you're solving a differential equation, you look at the order. That's what derivative is involved. Here it's a first order, so that says you should have one constant at the end. And so that's a nice way to remind ourselves that, hey, how many constants should we have at the end of the process? So if we have no constants, whoops, mistakes were made. If we have 8 constants, whoops, other mistakes were made. But that's all right. Learning to identify mistakes is a great way to get to the point where we don't make mistakes. So it's okay. It's all right. Now, all right, so we've separated, we've integrated, and at this point, we essentially have the solution. More particularly, we have the family of solutions. And it might be, okay, so that's the general form. Now, there's a couple of things that can happen here. One might be saying, well, find the family of solutions. And you're like, okay, that's it, life is good. Or it may say, find a particular solution. So finding a particular solution means solve for C. And it might say, oh, solve for the function y. Now you might say, okay, do I solve for C first and then solve for y? Or do I solve for y first and then solve for C? And the answer is yes. You can do either. So what's the right one? Well, it's not so much that there's a right or wrong. It's a matter of context. Which one is the easier one to do? That's the one that we start with. And I like to say my rule of thumb is you solve for C when it's convenient. And so if it's not convenient at a certain point to solve for it, hold off. Solve for it later. No one will be mad at you for doing that. And so I like to call this step, I call it my uncomplicate. Well, that's a made-up word, but that's all right. All words are made up. And why do I use that? Well, separate, integrate, uncomplicate. 8, 8, 8. And just a nice sort of cadence there. Keep in mind that sometimes when you're solving these, you might get an implicit function, especially if you have your y prime over g of y integrates to some very strange exotic function, and that's okay. Sometimes the best we can do are implicit functions. No worries. Life is good. All right. That's the whole idea. That's everything for today. And now the rest is practice. Practice. So let's start doing some practice. Practice. Our first example. Find the general solution for 1 plus 5y to the 4th y prime is equal to 2x plus 1 over x squared plus 1. All right. Now, what's going on here? It's separable. In fact, they already handed it to us in its separated format. So life is good. The only thing that we might do is to say, well, we could write this as 1 plus 5y to the 4th, and y prime is dy over dx. dy is equal to 2x plus 1 over x squared plus 1 dx. Okay, and now separated. Great, life is good. What comes next? Integrate. So separate, integrate. So we're already into step 2. So we're going to integrate both sides. Say, all right, well, 1 plus 5y to the 4th dy. So this is important notation, right? We really kept emphasizing Calc 1. Don't forget the d something. Don't forget the d something. Because you have to pay attention. What are you integrating with respect to? Here we're integrating with respect to y. So we say, oh, okay. Well, the integral of 1 with respect to y is y. Integral of 5y to the 4th, integral of that with respect to y is y to the 5th. And there we go. That's the left-hand side. And we'll put our constant on the right-hand side. Equals, now, what do we do with 2x plus 1 over x squared plus 1? All right, now you might say, aha, let u equal x squared plus 1. Then isn't the derivative of 2x plus 1? No, no, it's not. But what can we do? Well, let's just remind ourselves one quick thing, that when you see fractions, there's good addition and there's bad addition. The good addition is the addition upstairs. See, that plus sign upstairs is really convenient for us because a plus upstairs means we can pull it apart. So we can break it into two pieces. And so we can say, all right, this is 2x over x squared plus 1 plus 1 over x squared plus 1 dx. Now, the downstairs plus sign, this one right there, that's not a good plus sign because you can't pull apart addition downstairs. That requires more work, also known as partial fractions. In this case, partial fractions doesn't even apply. Whoa, what? All right, but what do we do? Well, now after you pull it apart, now we're in better shape because here you could say, oh, if you let u equal x squared plus 1, now we're good to go. Du is 2x. And so we have a du over u, which makes this a log of u, log of x squared plus 1. Oops, there's no more integral. We've already integrated. Got to be careful with the notation. Integral of 1 over x squared plus 1, classic arctangent. Gotta love it. And, of course, plus c. All right, and so we've integrated. All right, nothing too surprising, but we start with some more straightforward ones at the beginning. So what do we have? Well, we have y plus y to the 5th is equal to natural log x squared plus 1 plus arctangent of x and plus c. Now, we want the general solution. Can we solve for y? No, because it's involved in this expression. There's no way to solve for y simply in that kind of an expression. Nor is there a way for us to solve for x. But it doesn't say solve for x or solve for y. So we don't have to. It's just a general solution. And sometimes the general solution is an implicit function. And so the next step for us is to box. We don't need to solve for c because general solutions don't solve for c. Particular solutions solve for c, and we're not given initial values. So that's it. Life is good. Life is wonderful. So for our next example, find y of x, given that y prime is 3x squared e to the minus y, and y of 2 is equal to 0. So notice here, we want to explicitly solve for y, and we have an initial condition. So it's a little different from the one we just did, but that's all right. So what's the first step? Separate. Have we separated? Well, not yet. You'll notice we have both x's and y's showing up on the same side. And we still have that y prime, which I always like to think of as, hey, this is dy dx. All right, so what are we going to do? Well, what we'll do is we'll move things around. And in particular, we can move the dx across, and we can move the e to the minus y across. And if we do that, what do we get? Well, the dx, that's pretty simple. That'll give us our 3x squared dx on the right. When you move the e to the minus y across, what are you going to end up with? Okay, so how do you move it? Well, you could say I divide by e to the minus y. Dividing by e to the minus y is the same as multiplying by e to the y. So e to the y dy is equal to 3x squared dx. All right, good. Now, the next thing is we've separated, so it's the integration. Good news is these are pretty straightforward integrals. Integral of e to the y is e to the y. integral of 3x squared is x cubed. And of course, plus c. Now, we need to solve for c and we need to solve for y. Remember, we can solve in either order. And looking at it, we want to say, well, when we plug in x equals 2, we want y to be 0. We say, well, those are pretty nice numbers right now, so let's go ahead and solve for c right now. Because we can solve for c at any point. And the rule of thumb is we solve for c at the point where it's convenient for us to do so. All right, so here we go. Solve for c. We're going to get, so remember this is x, this is y. So we have e to the 0 is equal to 2 cubed plus c. Or e to the 0, also known as 1, is equal to 8 plus c. Or we can say that c is equal to -7. All right, so updating. We now have e to the y is x cubed minus 7. What's left? Well, we need to find y of x. We've already found the c, and the nice thing is there's just one y. So we say, okay, what can we do to get that y to get out of the exponent? In other words, what thing pulls stuff down out of exponents? And the answer is logs. So we can say the following: y, which is the natural log of e to the y, and we say, well, we know what e to the y is. That's natural log of x cubed minus 7. And put another way, we could say, oh, so y is the natural log of x cubed minus 7. And there we go. That's it. That's the problem. And, you know, not so bad, right? No, of course it's not bad. It's not bad at all. You just work the process. And there we go. Well, 2 examples down. Let's do some more. In our next example, we're asked to find x of t, given that x prime is t divided by 2x plus 4, and x of root 7 is 0. Now, of course, when you see unpleasant numbers there, usually that's a hint that when you plug it in, it will become pleasant. And so don't get nervous when you see weird numbers showing up. That's oftentimes like, aha, something nice will happen. Now we have to wait and see when that happens and what that'll be, but we're not nervous about that. All right, so where to begin? Well, all right, notice it's not y and x, it's x and t. No problem, right? No problem. So what do? Well, of course, we think of x prime is dx dt is t over 2x plus 4. And in this case, the separation is actually pretty straightforward. And we would call it, if you were doing algebra, we'd call it cross multiplying, right? Clearing out our fractions. I always love a good clearing out of fractions. And so we now have 2x plus 4 dx is equal to t dt. So we've now separated. Okay, after we separate, then comes integrate. So we integrate both sides. And what do we have? Well, we have x squared plus 4x is equal to, you know, straightforward, no surprises, 1/2 t squared plus c. All right. Well, what to do? What to do? Well, let's solve for c, right? Yeah, that doesn't seem like so bad, right? Because what does this say? This is our t, here is our x, and so when we plug in t equals square root of 7, we should get x equals 0. So, all right, so I'll switch colors here. since we're doing a slightly different thing. Now we're in our solve for C. So we have the following: 0 plus 0, because I'm plugging in x equals 0, is equal to 1/2 times square root 7 squared plus c. Well, of course, square root of 7 squared is 7. That's 7/2. 7/2 plus c is 0. Okay, so c is negative 7/2. All right, great, great. Progress, good progress too. Okay, so what can we do? Well, let's write what we have. We have x squared plus 4x is equal to 1/2 t squared minus 7/2. Are we done? And why not? We're not done. Well, why not? This is an implicit relationship right now. We're asked to find x of t. So we need to solve for x of t. Okay, well, how do we get x by itself? The nice thing is, it's looking kind of like a quadratic. Now, we could pull everything to one side and use the quadratic formula, or we can do a little bit of saying, hey, let's complete the square. It's about the same. I'm more of a complete the square because I say x squared plus 4x, I can make that look like a square if I do the following. Well, I take the 4, divide by 2, is 2, square it is 4. So if I were to add 4, that would make the left-hand side x plus 2 squared. Now, if I add 4 to the left-hand side, I have to balance it by adding 4 to the right-hand side. So this is 1/2 t squared minus 7/2. And if I add 4, I can write that as 8/2. So this 4 and this 8/2 are the same thing. Okay, good. So we now have x plus 2 squared is equal to, well, 8/2 minus 7/2 is 1/2. So that becomes 1/2. And I'll just go ahead and pull that out. Times t squared plus 1. Now, the good news is there's a single x. And so we just start pulling it out. Say, okay, how do we get rid of the square? Answer, square root. So x plus 2 is plus or minus the square root of 1/2 t squared plus 1. Or x is, subtracting, minus 2 plus or minus the square root of 1/2 t squared plus 1. Okay, is this our answer? And why not? You're right, it's not our answer. Why not? We worked hard, right? We did the work, we got there. Why can't this be our answer? Well, there's a sticking point. This is not one function, it's two. The plus minus. So there's a negative 2 plus something, there's a negative 2 minus something. We have to pick a side. Which one of these two is right? Which one of these two will give us the right answer? Or maybe are they both right? Now hopefully they're not both wrong. Now the claim is one of them works and one of them doesn't work. So which one is it and how can we figure out? What information is available to us? The initial conditions, right? So we already used the initial conditions once when we solved for C, but we can use it again. We say, look, we know when we plug in square root of 7, we need to get a 0. So I have negative 2 plus stuff, and I have negative 2 minus stuff. If I have negative 2 and I subtract things, I'm not going to get close to 0, I'm going to get more negative. Or if I put negative 2 plus something, then I have a real chance. Okay, so what we can say is that our initial conditions, namely that when we plug in square root of 7, we get 0, that tells us use the plus. So our final answer is x of t is negative 2 plus the square root 1/2 t squared plus 1. And that's our answer. That's it. We did it. Nice, nice. I like this one because you have to use the initial conditions more than once to help inform you. And I think that's a nice way to think about what's going on. All right, good. Well, let's move on and try another problem. So let's talk about Newton's law of cooling. So Newton's law of cooling says the following. The change in the temperature in an object is proportional to the difference between the ambient temperature and the current temperature of the object. And they actually gave us a formula here. And we said, oh, well, it would have been fun to figure it out. But let's see how this formula comes from this statement. Okay, so first off, the change in the temperature. Now, change is what? Well, change means derivatives. Derivatives are about changing things. And we're changing temperature, so that's T prime. So that's where that comes from. Now, the next thing we see is the word is. Is means equal. Okay, so change in temperature, T prime, equals something. Okay, moving right along. Proportional to. So proportional to means constant. So that's what, whenever you see the word proportional to, that means just, oh, hey, there's a constant involved. And finally, we say proportional to what? Well, the difference between ambient temperature and current temperature. So here, I'm looking at a difference. Difference means what? Subtraction between ambient temperature, which is the temperature of the, say, the air around you or whatever you happen to be. Maybe it's water. But the ambient subtract current temperature. And that's it. That's it. So you can see how each part of this sentence becomes a part of the differential equation. That's not so bad. No, it's not. Nor is this like a crazy idea. You're like, that seems kind of obvious. Because what does it say? It says, hey, if I'm a very hot object in a very cold environment, my temperature should change pretty rapidly, whereas compared to, say, I'm a lukewarm object in a lukewarm environment, my temperature won't change very much at all. And that's really what the idea. The bigger the temperature difference, the faster your temperature change. You would think Newton really gets to be called Newton's law of cooling for that simple idea? Well, yeah, because he was the first one who came up with it. Just because it's has a name doesn't mean it's complicated. Most ideas aren't. In fact, most good ideas are simple ones. So don't use a complicated idea when a simple one works just as well. All right, so now the question is, we have Newton's law of cooling. What can we do with it? In other words, here we have a differential equation that describes temperature change. What's the actual way that the temperature changes? So we need to solve this. So now, of course, part of our problem is we have temperature, which is T, and we have time, which is little t. So we have to learn to write well enough to make sure we distinguish the two. So change in temperature with time is, now you can write it as proportional to a minus t or as minus k times t minus a. Now, mostly this is just a matter of what sign do we want. Because we say, okay, what should be true? Think about our saying again. I'm a hot object in a cold environment. So the ambient temperature minus the current temperature would be a negative number. And what should be happening to my hot object? It should be having it go down in temperature, should be cooling, and hence the sign change. So this is mostly just to make sure the sign works out. So oftentimes if you're saying, what's the right sign? Just think of a simple situation. A lot of times thinking about a simple scenario helps figure out, oh, I see what's going on. Okay, no problem, no problem. Now I'm going to use this second variation. The only difference here is you pulled out a minus sign. That's okay. That's no problem. And the reason I prefer this variation is I like to have my t be positive. So k is some constant, just depends on the scenario. A is again some constant, it depends on the scenario. So A is your ambient temperature, and K is just depends on how quickly the object interacts with the surrounding environment. Okay, so is this separable? Well, yeah, it's actually pretty easy to separate because there's no little t, and this can be moved across. So we say, okay, so this is the same as d capital T, change in temperature, over T minus A is equal to minus K d little t. So there we go. We have successfully separated. Now we want to successfully integrate, because that's our next step. The integral of dt over T minus A will be natural log of T minus A. Integral of minus K dt is minus K times T, and of course, plus C. Now, do I want to plug in my constant here or plug in my constant later? Looking at this, when I plug in little t equals 0, big T equals T0, it's not looking pretty. So I'm going to hold off plugging in my constant and solving that later. It's okay. It's my choice. Both ways will get the right answer. It's just a matter of saying, you know, do you want to keep things simple now or just sort of drudge along with what you get? And I'm a big, let's keep things simple. All right. Now the goal is to solve for t. And how do we know that's our goal? Well, it says it. That's a pretty good clue. The nice thing is there's only a single t. So we need to get that t out. So taking the exponential function, plugging both sides in, well, e log are inverses of each other, so we end up with t minus a. Now here, on this side, we say, well, hey, look, this is the same as e to the minus k times t times e to the c. And e to a constant is a constant. Constants can absorb constants, so I can say, well, I'm going to rewrite this, and, well, I have a tendency to use the same letter, but secretly, I've sort of rewritten C. That's what's happened here. So that what we used to call e to c is now what we're calling c. If that's uncomfortable for you, that's okay. And I understand that. Call it d. Life is fine. All right. So we have t minus a is some constant e to the minus k t. And we say, aha, that says our temperature is a plus some constant c e to the minus k t. Now, are we done? Not yet, because we haven't plugged in our initial condition. We said we were going to wait for it. Well, no time like the present, because there's nothing else for us to do on this problem. So what do we have? We have t0 is equal to a plus c e to the 0, because we're plugging in little t equals 0 and big T equals T0. Well, e to the 0 is 1, so that tells us that c is T0 subtract a. And now we get t is a plus T0 subtract a e to the minus k t. And that's it. All right. Now, before we leave this, let's ask the question, is this a reasonable answer? So let's think about our setting. We have our object. I've been describing it as a hot object in a cold space. Fine, let's stay with that. The space doesn't change. So in other words, having a hot object in there doesn't somehow make the space now become a warm space. It's always going to stay the same. So keep that in mind. So what's going to happen to the object? What should it do in the long run? Well, it should start to behave like the environment it's in, right? In other words, it should warm up or cool down, depending on the scenario, to match its surroundings. Does that get reflected in this? Well, in the long run, e to the minus kt does what? The answer is it goes to 0. So in the long run, that part goes away and it approaches the ambient temperature. Good, good. So it is doing what we expect. You might also think, what about K? Well, K is somehow capturing how much interaction there is. So a larger value for K should mean that our object is interacting with its environment a lot, and that should drive the temperature difference to be faster, right? It should be like, oh, I should more quickly become my ambient temperature. A low value for K says it's hard for the object and the environment to interact, so there should be a slow change. That is again reflected here. Because if you have a very large value for K, that says it's an exponential function which is going faster to 0. And if we have a very small value for K, it's an exponential function that goes slower to 0. So, you know, it makes sense. It matches with what we think it should do. And in particular, if you were to graph this, what you would see is that you have your ambient temperature and you just sort of head towards it following an exponential function. You don't like somehow jump back and forth like, now I'm warmer, now I'm colder, no, no, no. You just head towards the ambient. All right, good. Let's do one more problem. This is one of my favorite problems. And if I ever do die and I get a gravestone, I hope something like this will be on my gravestone, just because I've had so much fun writing this one. And in case you're wondering where this comes from, this is based on a story by Dr. Seuss. So here we go. Now the star-belly Sneetches had bellies with stars. The plain-belly Sneetches had none upon theirs. Then one day, Sylvester McMonkey McBean came to town with his wondrously wonderful machine. Just one pass through, hop on board, and you will have a star for sure. The Sneetches listened, and the Sneetches thought, and those who wanted a star belly stepped up and bought. Sylvester kept track of the proportion of Sneetches with stars, we call that P, and noticed with time, T, in months, that P prime is 1/3 T times 1 minus P squared. Now on a side note, in the actual storyline, there's no differential equations, but we had to put that in. All right, so here we go. His business was quick, he did not want to delay, and so he recalled on his very first day that P equals 1/4. To make a quick buck and then leave this place, he decided to leave when P equals 3/4. How many months then will it take until Sylvester McMonkey McBean leaves this place? I love this. Okay, now, if you don't, that's okay. We can extract what we need. So how do you go about extracting what you need? Oftentimes the key thing is look for math things. And we see there's a couple of math things right away. There's a differential equation, there's some initial condition, and there's a goal. And if that was all you saw, then that's all you needed. So then you say, well, what's the rest of this? Fun. And shouldn't math be fun? I hope so. You know, that's why I became a mathematician, because I like having fun. All right, so here we go. Here we go. So what do we have? Well, we have P prime is equal to 1/3 T times 1 minus P squared. All right. Now, notice this is a separable differential equation. Well, no surprise. I mean, that's our discussion for today. And so let's separate. So dp, and we'll move the 1 minus p squared across, is equal to 1/3 t dt. All right. Now we have separated. Not much had to be done. We moved the dt across, moved the 1 minus p squared across. Okay, cool. What comes next? Well, it will not surprise you, is integration. Now for this one, let's think about rewriting it in an integration-friendly way. Now 1 minus p squared, you can notice the square, it doesn't matter whether it's 1 minus p or p minus 1 when you square things. So we can say, hey, you know what? That's the same as p minus 1 to the minus 2 power. Yes? Cool. All right. Sounds good to me. And dp, all right, equals, now 1/3 t, well, that's not too bad, because I can integrate t. So that's 1/6 t squared, and of course, add on a c. Now, the reason I want to rewrite it is I want to rewrite it into a way that's calculus friendly, where we have our rules. And in this case, we say, hey, you know, this part, I know how to integrate that. I add 1 to the exponent, divide. And so it'll become 1 over minus 1 makes a minus. And then we have p minus 1 to the minus 1 power equals 1/6 t squared plus c. Or, if you like, I can write this as 1 over p minus 1, but there's a negative, so I'll write it as 1 over 1 minus p. Now, there we go. So there's our integration. What comes next? Well, we have initial conditions. Now, how do we know it's our initial conditions? It's on the very first day. So that sounds pretty initial to me. Hard to think that the very first day was not near the beginning. So we say, okay, so plug in p equals 1/4 and t equals 0. What do we have? Well, 1 minus 1/4 is 3/4. That's downstairs. 1 over 3/4, you flip it, becomes 4/3 equals, and then 1/6 times 0 is 0 plus c. All right, well, that was really quick. So now we go. There we go. 4/3 equals c. Okay, so updating. 1 over 1 minus p is equal to 1/6 t squared plus 4/3. Okay, good, 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 good. Now, what are we looking for? Well, we're trying to find a time. How do we know we're trying to find a time? Because there's a question, how many months? That's time. So we're trying to find a time when we hit p equals 3/4. Okay, so in other words, we're plugging in p equals 3/4, and what's the time? So we say, okay, what can we do? Well, we'll do what we just did, right? We have 1 over 1 minus 3/4. So 1 minus 3/4 is 1/4, which becomes 4, because we flip it. So 4 is equal to 1/6 t squared plus 4/3. All right, well, let's subtract 4/3. Actually, no, let's just make life easy. Let's multiply by 6, so we get rid of fractions. So 24 is equal to t squared plus 8, right? Yes? Because I multiply by 6 comes 24. The 6 cancels on the t squared, and 4/3 times 6 is 8. And then we can subtract 8. So that tells us 16 is equal to t squared. And now we can take the square root, and we discover, lo and behold, t equals plus or minus 4, Well, of course, you know, Sylvester McBean's machine may be wondrously wonderful, but it doesn't go backwards in time. And so we need to have the positive, not the negative. So it's the positive 4. And we know that t is measured in months. And so Sylvester McBean will be staying there with his wondrously wonderful machine for 4 months. And we're done. Now you might say, wait, we never solved for p. No, because we didn't have to. We used information to figure out what our answer should be, and that's perfectly fine. The key here is make sure you know what you're asked to solve for, and if you don't need to do it, you don't have to. We only do things when it's convenient for us or if we're told. And sometimes what we're told to do is not always convenient, but that's okay, because we're going to just go ahead, follow the instructions, and get all the points. Got to get them all. All right, well, that's our practice. And of course, you should get some practice too. All right, see you again. Bye.